G'day and welcome back to Mathematics for another free maths lesson in the Extension 1 HSC course. Today I'm going to take you through my first two lessons in the binomial probability distributions topic, saving the third one for a video next week because it's pretty hectic, so it will definitely need its own video. Okay, let's get stuck in by getting some terminology down, and then once we have all the notes covered, I'll show you a bunch of examples and give you an idea of how to tackle these kinds of questions should they arise in your pesky little HSC exam. Starting off with just what a Bernoulli trial is. So a Bernoulli trial is any probability experiment where there's only going to be two distinct outcomes: pass or fail, right or wrong, heads or tails. I don't know how Mr. Bernoulli managed to get a coin flip named after him, but there you go. Heads on a coin, 5 on a die are two things that you can either succeed or fail at, so they're considered Bernoulli trials. Another one could be making it through your 2024 HSC with or without a complete mental breakdown. Hopefully with enough mathematics, you'll be leaning towards success rather than failure. All right, so for these examples in today's video, P is going to be our probability of success. And so because there's only two outcomes, the other outcome is failure, which is 1 minus P. So these two together make up the entire sample space. Okay, let's say, to give you an idea of how these repeated Bernoulli trials work, we're going to flip a weighted coin where the probability of heads is X and the probability of tails is Y. May or may not be 50-50 depending on the weight. We're going to flip the coin 3 times and we're going to have a look at what the sample space of all possible outcomes looks like. So after one coin flip, we either have heads or tails. So the sum of our entire sample space would be either X or Y, so X plus Y in total. Okay, now we flip the coin again and we get some more branches to our probability tree. Now we have 4 outcomes. We could have X and X, X and Y, Y and X, or Y and Y, which looks like this. Now X times Y and Y times X are the same thing, so we group them together into a familiar identity, which is the expansion of X plus Y all squared, your perfect square. Leading into what's going to happen when we flip our third coin and get a bunch more branches. We now have 8 total outcomes. I'm not going to run through them all, but as you can imagine, they're going to look something like this. We could either have heads 3 times, heads twice, and then tails once, so on and so forth. Here are all the multiplications from our 8 branches. Now, putting together all our like terms, like for example, x squared y can go with x y. So we can group them all together, and what we end up with is x cubed, 3x squared y, 3xy squared, and y cubed. Now this is, uncoincidentally, the exact same thing as the expansion of x plus y all cubed. So our total sample spaces, all our outcomes, are all following the pattern of a binomial distribution, which is why we would know, without even sketching, that after 4 trials, 4 flips of this coin, our total sample space would look like this, because this is the next row of Pascal's triangle. So this is brilliant, because now if we're trying to find the probability of an event where there's only 2 outcomes, all we need to do is just do how many times we want success, how many times we want failure, and how many times we can arrange those successes and failures using combinations. So we have, for example, in the third trial row, we have 3C0, 3C1, 3C2, and then 3C3 as our 4 coefficients. So that's a really cool shortcut, and that's how we're going to answer these questions today. So the information for repeated n Bernoulli trials, it follows the structure of a binomial expansion, which means if you want to find the probability of something happening x times with a probability of p, we do success to the power of however many times you want it to happen. And so failure must make up the rest of the trials, and then we multiply that by how many times the successes can be arranged in n total trials. If that makes no sense right now, don't worry. Once we do a few examples, you know exactly what I'm talking about. Here's a quick one to start us off. If I wanted to find the probability of rolling a die 7 times or rolling 7 dice, and I want to find the probability of seeing 5 exactly 3 times. Well, 5 has a 1 in 6 chance, and I want that to happen 3 times, which means I need failure, which is not a 5, which is a 5 in 6 chance. I need that to happen 4 times. The number of ways I can arrange 3 successes out of 7 trials is 7C3. So here's the structure we're going to be creating today to answer all these questions in a convenient and beautiful mathematical way. Let's dive into some examples. This is from the 2018 HSC. We have 12 people setting off on a trek. The probability that any person finishes the trek within 8 hours is 75%. Find an expression for the probability that at least 10 people from the group complete the trek within 8 hours. So out of 12 people, we want to find the probability of at least 10 successfully completing this trek within 0.8 within 8 hours. So for at least 10, there's a few ways we could do that, because we could have 10 people complete it, we could have 11 people do it successfully, or we could have all 12 successfully completing the trek within 8 hours. So we have 3 things to calculate here, and then sum together and get our total answer. Notice for a lot of these questions, they say find an expression rather than a decimal answer, because quite often the decimals are, very long and gross. So usually the working out is the correct answer. Okay, starting off with the probability of 10 successes. That means we need this event that has a probability of 0.75. We need that to happen 10 times, and then we need 2 people to fail. So we have 0.75 to the power of 10. That's our 10 successes. Failure is 1 minus 0.75, which is 0.25. We need that to happen twice. And the number of ways we can arrange 10 successes in 12 trials is 12C10. Following that structure for the probability of 11 people successfully doing it within 8 hours, we're going to have success probability to the 11, failure probability to the 1, and then 12C11. For the last one, it's much of the same thing again. However, you can shorten this because we have 12C12, which is just 1. Okay, the first and last coefficients of any row for a binomial expansion are always 1. And we have 0.25 to the power of 0, which is also 1. So for this last one, the probability of 12 successes, we could have just done 0.75 to the power of 12 to be a little bit more efficient, I suppose. Anyway, here is our expression for the probability. If we do a bit of calculation, we'll get an answer of approximately 39%. But as I said, the working out is an expression, and that's going to be getting us our full marks for questions like this. Okie dokie, on to the next one. We have prize-winning symbols from the 2019 HSC. They're printed on 5% of ice cream sticks, like you used to get in paddle pops back in the day. Maybe that still happens. I don't know. I'm old. The ice cream sticks are randomly packed into boxes of 8. What is the probability that a box contains no prize-winning symbols? So we have 8 in a box. Any of those 8 have a 5% chance of a prize. So what's the probability that we get no prizes 8 times in a row? Well, probability of no prize would be 95%, because it's either pass or fail. So we need 95% to happen 8 times, which means we need to do 95% to the power of 8. Okay, again, when every single trial is succeeding, or when every single trial is failing, you don't need to do all the combination stuff because they're just going to be 1, so you can save yourself some time. Okay, question B, what is the probability that a box contains at least 2 prize-winning symbols? Now this is tricky because there's a lot of ways we could do that. We could have 2 prize-winning symbols, we could have 3, 4, 5, 6, all the way up to 8. So we're going to need to think of a shortcut here. Rather than calculating the probability of 2, up to 3, up to 4, up to 8 prize-winning symbols, it's going to be quicker if we just find the probability of having 1 prize and then 0 prizes, and then taking that away from 100%. All right, so the cool little shortcut we can use is to find the probability of x being greater than or equal to 2, x being number of boxes with at least 2 prize-winning symbols, is we can just do 100% and then take away the probability of no winning prizes and then take away the probability of 1 winning prize, leaving us with the rest of the sample space, which will be 2 or more. So you got to work smarter, not harder on these examples. All right, so probability of no prize-winning symbols is what we've already done in part A, which was a hint as to why this is the best approach. So all we've got to do is find the probability of getting 1 prize-winning symbol. So there's our 0 from part A, no prize-winning symbols. And here's 1. We need to have a 5% chance happening once. That's our success happening once. We need failure, and that should say 0.95, and that's a typo. So don't write that down. Write 0.95 to the power of 7. And the number of ways we can arrange this 1 success amongst 8 trials is 8C1. Which means this answer will probably be wrong, so don't write that down, but change that to a 0.95 power of 7, and that will get you the correct answer. Weekly reminder that you get what you pay for at Mathematics. Thanks for watching. Hope you're learning. All right, moving on to example HSC question from 2023. Alrighty, this one's a band 4, so it's a mid-level question. We have 9 pieces of equipment at a gym, which is cool. I wouldn't know, never been inside one. 5 treadmills and 4 rowing machines. On average, we have a treadmill used 65% of the time, and a rowing machine, less popular, only used for 40% of the time. So let's find an expression for the probability that at a particular time, 3 of the 5 treadmills are in use. Okay, so we need a 65% chance event to happen 3 times, which means the other 2 treadmills need to be not in use. So 65% chance of being in use means a 35% chance of not being in use. And then we need to multiply that by the number of ways we can arrange these 3 successes in a total of 5 trials, which is 5C3. So as long as you know how to set up a binomial probability, this is actually a very straightforward 2 marks, getting us an answer of something. Notice I didn't calculate it because it says find an expression, so you don't need to actually calculate the decimal. This is a correct answer for 2 marks. All right, and part 2, find an expression for the probability that at a particular time, 3 of the 5 treadmills are in use. Already done that, awesome. And no rowing machines are in use. All right, so we've already got our 3 treadmills being in use, probability by like right up here. We just need to multiply that by the probability that no rowing machines are in use. So a rowing machine is in use 40% of the time, which means it's not in use 60% of the time. So we need a 60% likely event to happen. We've got 4 rowing machines. So we're going to multiply that by itself 4 times. So 60% chance happening 4 times. So here's our no rowing machines. Here's our 3 out of 5 treadmills. We want both of them to happen. So we are just going to multiply them to get our total probability outcome for 1 mark. Okay, there you go. That wasn't too scary. Let's look at an actual scary one. This one has been haunting my dreams for 13 years now because I actually did this question in 2011 and probably got it wrong because I wasn't good at maths until I was like 23. Anyway, a band sixer from 2011. We have a game played throwing darts at a target. Sounds fun. We can choose 2 or 3 darts to throw. In game 1, you're going to throw 2 and you win if you hit the target at least once. In the second game where you're throwing 3 darts, you've got to hit the target at least twice. The probability we hit a target with any throw is P, and P is between 0 and 1, not inclusive. Okay, part 1. Show the probability that Darcy wins game 1 is 2P minus P squared. Alrighty, let's dive in. We're throwing a dart, we're throwing 2 darts, and we want at least one of them to hit. So there's a couple of ways we can do that. We could either hit the first dart and then miss the second, or we could miss the first, hit the second, or if we're on an absolute heater, we could hit both of them. So probability of hitting is P, which means the probability of missing is going to be 1 minus P because these are Bernoulli trials, as we say in the business. So probability of hit times miss plus probability of miss times hit. And then on the end, we have hit times hit, P times P. All right, if we expand this all out, we get P minus P squared, we get P minus P squared again, and we get P squared on the end. 2 of the P squareds cancel out, the 2 P's go together, like 2 P's in a pod, and we get 2P minus P squared as required. All right, we're off to a flying start. Let's try the next part, which is game 2. Show the probability that Darcy wins game 2 is 3P squared minus 2P cubed. So in this one, we are throwing 3 darts, and we've got to hit 2 of them. All right, a few ways we could do that as well. We could have 2 hits and 1 miss, or we could have all 3 hitting. So rather than doing, hit, miss, hit, hit, doing all the different calculations, let's use the magical shortcut of binomial probability. We want success twice and then failure once, and we're going to multiply that by the number of ways we can arrange those 2 successes out of 3 trials. You're seeing the same structure every single time. So probability of 2 hits is P squared. Probability of 1 miss is 1 minus P, and then arranging those in 3C2 ways. 2 successes from 3 trials. For 3 hits, we can simply just do P times P times P, which is P cubed. All right, so 3C2 is actually 3, fun fact. So we have 3P squared, 1 minus P plus P cubed. Now we're just going to expand that out and simplify, and we get 3P squared minus 3P cubed plus P cubed, which simplifies to the target for a nice little 1 mark QED. 3P squared minus 2P cubed. Okay, now we get into the fun part, the real band 6 stuff. Prove that Darcy is more likely to win game 1 than game 2. So show that 2P minus P squared is greater than, more likely than, 3P squared minus 2P cubed. Oh my God, I love inequalities because I love extension 2. All right, let's put all these on one side because it's usually much easier to compare something against 0 rather than something against other algebra. All right, so everything on one side looks like this. We have the 2P cubed over here. We have minus 4P squared by collecting like terms, and the 2P is still here. All right, I'm seeing some common terms. I really would love to factorize, so I'm just going to do it. I'm going to take 2P out of everything, leaving me with P squared minus 2P plus 1, which is lovely. All right, so I have 2 things multiplying, and I need to explain why they are greater than 0. It's easy to explain why 2P is greater than 0 because P, as stated in the question, is a probability, so it's going to be positive. Okay, so 2P is positive because P is positive. Now for the p squared minus 2p plus 1, conveniently, this factorizes to a perfect square, and we get p minus 1 squared. Now the question also stated that p was bigger than 0 but less than 1, which means that p minus 1 is not 0 because p is not 1. So something in here is being squared, so this is obviously going to give us something positive because p is not equal to 1 and because this is going to be bigger than 0. So there we go. We have two things multiplying. They're both shown to be greater than 0, so their product must be greater than 0. So everything flows logically from bottom to top, and the original statement was proven true. So there we go, QED. All right, that was fun, and even more fun lies ahead with part 4 for our last 2 marks. Yes, find the value of P for which Darcy is twice as likely to win game 1 as he is to win game 2. So we're going to find a value of P that makes the probability of game 1 equal to 2 times the value of the probability of game 2, because game 1 is twice as likely. So game 1 is equal to double the probability of game 2. That's how we set up the equation. This time it's not an inequality, this time it's a quadratic equation that we can solve because we passed year 10. So we're going to expand the right hand side to get 6p squared minus 4p cubed. We're going to group everything together on the left hand side to make it look a little bit more quadratic-y. So the 4p cubed goes over to the left to become positive. We're going to take 6p squared off both sides to get minus 7p squared. 2p is still here and positive. Okay, now we can factor a p out of everything to look like this, but we still have a 4, a minus 7, and a 2 with no common factors, all right? And this is actually a quadratic that cannot be factorized. We have to bust out plan B, which is the good old-fashioned quadratic formula. A is 4, B is minus 7, and C is 2. So chucking those 3 values into our quadratic formula, we have negative 7 plus or minus the square roots of negative 7 squared. Take away 4 times 2, all over 2 times 4, sorry, which is 8. Simplifying inside our square root, we get 49 take away 32, which is 17. And so we get 2 options. Either P is 7 plus root 17 over 8, or P is 7 minus root 17 over 8. Now the problem with this answer is that probability answers always need to be between 0 and 1. And actually, if you calculate 7 plus root 17 over 8, you get a value that is bigger than 1, which is not mathematically possible in the context of this question. So the only valid solution for this one, to give our final answer, must be the minus, and that should be an 8. So that's our second typo for today, and we're only halfway through. I am nailing this. So final answer should be 7 minus root 17 divided by 8. My apologies. Okay, that's the binomial probability section of the lesson done. Let's move on to looking at binomial distributions to give us some useful formulas that we're going to be needing in the hectic lesson that I warned about next week. So starting off by calculating the mean and variance of a Bernoulli trial. Bernoulli trial having a probability of success P, probability of failure 1 minus P. We're going to call 1 a success and 0 a failure. So the way we calculate the expected value of a discrete probability function is we take our outcomes, which in this case are 1 and 0, and we multiply them by our outcomes, our probabilities, P and 1 minus P. I have videos on this in the advanced playlist if you need to brush up on this stuff, but again, the proofs aren't really important, it's just the formulas that we're going to need. So 1 times P plus 0 times 1 minus P. This ends up with just an expected value of P. All right, so the expectation, the mean, as you might call it, is just the probability of success. Now to find our variance, we've got to do the expectation of our outcome squared minus the expectation squared. So for the first part, we're doing the same thing again, but we're squaring the 1 and we're squaring the 0, which doesn't really do much. For the second part, we're taking the answer from the expectation, which is P, and we're squaring it to make it P squared. Okay, when you simplify this whole out, you get P minus P squared, which factorizes to P 1 minus P. So our expected value of a Bernoulli trial is P, and our variance is P times 1 minus P. So relating that to a binomial distribution, which is just a repeated version of the Bernoulli trial, we get these formulas. Okay, so because these are our Bernoullis, if we multiply them by n different trials to make it a binomial distribution, we get our expectation, our mean, is P times n, and our variance is P times 1 minus P times n. So it's the same thing as before, just multiplied by the number of trials. This notation here is saying that X is following a binomial distribution with a mean of, with the number of trials N and success probability P. Although looking at that, I think they're meant to be flipped, but it's probably not going to matter right now. Okay, and don't forget, whenever you want to find the standard deviation, which is going to be really, really useful for the next half of this topic, you've got to do the square root of your variance. So let's run through a few examples of showing you how this stuff works, and then we'll be all ready to finish off the topic when I see you guys next week. And a lot of this information, fortunately, is on the reference sheet, so you don't have to memorize it. It gives you the standard setup for a binomial probability outcome. It gives you the notation, and it gives you the expected value and the variance of a binomial distribution. So you don't need to memorize these. Formulas are here if you can't remember them, even though they are pretty straightforward. Okay, first example. Find the probability of rolling 2 dice and obtaining 2 numbers with a difference of 2. Alrighty, when you roll 2 dice, there are 36 outcomes because the first die has 6 and the second die has 6. Number of ways you could get a difference of 2, or you could get a 1 and a 3, a 3 and a 1, a 2 and a 4, a 4 and a 2, a 3 and a 5, and a 5 and a 3. So that would be 8 different ways of doing that out of 36 possible outcomes. So the probability that you roll a die, 2 dice in fact, and see numbers with a difference of 2 would be 2 out of 9. Okay, 2 dice are going to be rolled 50 times, so we're repeating our binomial trial 50 times. Find the mean and variance for the number of times the numbers have shown a difference of 2. All right, so let's use our formulas. First one is the mean of a binomial distribution is number of trials times probability of success. So we're going to do 50 trials with a probability of success being 2 out of 9. 50 times 2 out of 9 is roughly 11. So the average amount of times we expect this to happen out of 50 trials would be 11 successes. Now for our variance, we're going to do NP, which is the same thing as before, but we're going to multiply it by 1 minus P. So we have N is 50, P is 2 out of 9, which makes probability of success must be 7 out of 9 because it's the complement of the 2 out of 9. You guys know that. Calculating that, it's roughly 8.64. So if we wanted to find the standard deviation of this distribution, we would do the square root of 8.64. So nice friendly one to start off. Let's go on to the next one. Next one, we have a standard 6-sided die being rolled 10 times. The number of times a prime number is shown follows a binomial distribution because you can either roll on a prime or you cannot. So it's 2 distinct outcomes. Find the standard deviation of n, correct 3 decimal places. All right, when you roll a die, what's the probability that it lands on a prime number? I know this is controversial, but 1 is technically not a prime number. I don't know why. Actually, I do know why, because it only has 1 factor, not 2. So out of your first 6 digits, your prime numbers would be 2, 3, and 5. So your success probability would be 3 out of 6, or a half. Our number of trials, we're rolling this die 10 times, so n is going to be equal to 10. Okay, so to find our standard deviation, we first of all need to find our variance. So we're going to use our variance formula, np times 1 minus p. Okay, so n is 10, p is a half, which means that 1 minus p is also a half because this is success and this is failure. 10 times a half would be a quarter of 10, which is 2.5. So variance is 2.5. So to calculate our standard deviation, all we need to do is the square root of our variance. That Greek letter there is sigma, which we're going to be using quite often. I know it's a hilarious word, get over it. Sigma, so we're going to need to do the square root of 2.5, which to 3 decimal places is 1.581. So there you go, just getting more comfortable using these formulas because these calculations are going to be the initial steps of some more complicated questions towards the back end of this topic. Okay, up next is example 3. On average, batsmen playing in a T20 competition play a scoring shot 2 out of every 3 balls. In a regular season, a total of 1,200 6-ball overs are bowled. Estimate how many overs would have at least 5 scoring shots. I hate cricket. All right, so let's figure this out. We need to find the probability that in an over, which is 6 balls being bowled, whatever, sports, estimate how many would have at least 5 scoring shots. So there's 2 ways we can do that. We could have 5 scoring shots out of 6 in the over, or we could have 6 scoring shots out of 6 in the over. So we need to calculate both of those and then crash them together. So let's start off with that. So X is number of scoring shots in an over. We're trying to find the probability of scoring shots being 5 or bigger. So the way we're going to do that is by calculating 5 and calculating 6 using a binomial calculation. All right, so for our 5 successes, we have It says we hit a scoring shot on 2 out of every 3 balls. That means our success probability of hitting or playing a scoring shot is 2 out of 3. We want that to happen 5 times, which means we need to not score on 1 occasion. Multiplying this by the number of ways that 5 successes can be arranged in 6 trials, which is 6C5. Okay, then for 6 successes, again, we can just do the shortcut of just success probability to the power of 6. We don't need to do the other calculations because they're going to be equal to 1. Okay, putting these together gives us a probability of 256 out of 729 number of scoring shots. Okay, so there is our probability of success. So now if we consider that Y, for example, could be number of overs with greater than or equal to 5 scoring shots, our success probability is 256 out of 729, and the number of times we're trying this is 1200. We're bowling 1200 6-ball overs. So here's our binomial. We've got our P and our N and our P. And so now to find our expected value of this distribution, as before, we're doing number of trials times probability of success. So multiplying these two figures together, getting us 1200 times 256 out of 729 is going to estimate us 421 overs approximately of getting greater than or equal to 5 scoring shots. All right, so hopefully you're seeing that when you're doing a lot of these questions in succession, you're seeing the same pattern, the same kind of terminology, and the same formulas over and over again. So once you get comfortable with them, you're going to be able to handle anything the HSC throws at you. Probably. I can't guarantee it. Okay, what's up next? We've got example 4, surely HSC time. HSC time. All right, this one is a really hectic band 5 from 2022. It's actually harder than the band 6 that we did before, in my opinion. There's a lot going on here. We have a game selecting 4 balls from a bag. Each ball is replaced back in the bag. 3 red balls and 7 green balls. Each red ball gets you 10 points and every green ball loses you 5 points. So if we had 3 red and 1 green, it would be 3 times 10, take away 1 times 5, giving you 25 points in total. What is the expected score in this game? Okay, so unpacking this, expected score is essentially the same thing as expected value. And the way we calculated expected values before in the intro is we did all of the outcomes times by their probabilities. So we need to find the probability of all our different scores and then multiply them by their scores and then add the whole thing together. Okay, so we're doing probabilities times outcomes and summing them all together to get a total. So we got to dive in because we've got a lot of probabilities to calculate. This is a massive question for 2 marks. I really think it should be 3, unless there's a really cool shortcut that I'm not seeing. If there is, let me know in the comments and I'll do my homework. Okay, starting off with, we're just going to say X is equal to the number of red balls. You could do red or green, but I think red is a bit easier. Now, let's think about the score when X equals 4. So the score is, well, when you get a red ball 4 times, is that possible? Oh, yes, sorry. Just rereading the question. Because the balls are replaced each time, so it's not like you can pull out 3 and then have none left. You can pull out 4 red balls in a row. Each time, because there's a 3 out of 10 chance of getting a red ball, it's a 30% chance. We want this to happen 4 times in a row, so we're doing 30% to the power of 4. And then if we had 4 red balls, every red ball gets us 10 points. So we would multiply this probability by its outcome, which is 40. Okay, 0.3 to the power of 4 times 40 is 0.324. So there's our expected score from probability times outcome for number of balls. Okay, now let's think about when X is equal to 3. So we get 3 red balls. So we could have the 30% chance happening once, which means, we have the 30% chance happening 3 times, which means we have the 70% chance happening once, multiplying this by the number of arrangements of 3 in 4 options, so 4C3. This is 3 red balls. That would be getting us 10 points 3 times, and then it would be losing us 5 points once. So 10 plus 10 plus 10, take away 5, as they said, is 25. So our outcome would be 25. So we're doing probability times outcome, getting us an expected value of 1.89. Okay, now we're going to do this a few more times because we've got to do 2 and then 1 and then 0 red balls to get all 5 possible scenarios. So again, a lot of work. Let's just run through it quickly. Here's the probability of getting 2 red balls, the same expression as before, just with some different values. Success happening twice, and so failure happening twice for C2. If we have 2 red balls and then 2 green balls, we're going to gain 20 points and then lose 10 points. So it would be a 10 points outcome. Probability times outcome is 2.646. Okay, calculating the last two. computer's starting to struggle a bit. It's been a long day. All right, so one red ball would be 30% happening once, so green happening 3 times. One red ball is 10 points, and then we're losing 5 points 3 times, giving us a net of -5. So this is starting to be bad. Probability times outcome, -2.058. And then the last scenario is when we are having no red balls. We're just getting green balls happening 4 times, and every green ball loses us 5 points. So we've just lost 20 points, which is horrific. Probability times outcome, -4.802. Okay, here are all our expected outcomes. Like before, we do probabilities times outcomes, and then we add them all together. If we add all these figures together, we get a total expected average value from this game of -2 points. So it's not a very good game. On average, every time you play, you are going to lose 2 points. So it's like we're back at the casino. Okay, that's it from 2022 for Band 5, and that's it for this lesson. Thanks so much for watching, and I'll catch you next week for the remaining content in this topic, which is normal approximations of sample proportions. It'll be a good one, so buckle up, and I'll see you then. Thanks for watching. Catch you soon.